Last class we started with the DC to AC converter, then we start with the single phase, the basic configuration half bridge converter, then how we will be able to get a rectangular pulse of equal on and equal of duration, and how it depends on the DC link. Okay. Then we found that for DC to AC, that means for AC waveform we have to control both frequency as well as the amplitude. The amplitude depends on the what we are talking about. The amplitude is the fundamental component, and for the previous pulse waveform like this type of rectangular pulse, what we found that by varying the S1 on and S2 off, we can control the frequency, but we will not be able to control the fundamental. Okay. Then from the half bridge we introduce one more leg here, S3, S4. Okay. Then the load is connected between A and B. So, A is called this whole leg is called the single pole double throw switch. So, pole A and pole B. So, the total voltage, the net voltage coming across the load is VA0 minus VB0. So, here we said for the pole voltage A0, when it goes to minus VDC by 2 plus VDC by 2 minus VDC by 2, the total load voltage waveform, it will go from plus VDC to minus VDC. So, that way we have increased the amplitude, but here the frequency can be controlled by controlling the S1 on and then S1 off here and S2 on here. Okay. So, how to control the voltage? Okay. And we previously also we talked about the fundamental and the harmonics. This will have fundamental, third, fifth, all harmonics, and the harmonic amplitude will be inversely proportional to its harmonic order. Okay. Then we said we found out that for controlling the voltage as well as the frequency, we require 2 degrees of freedom. So, by turning on S1 and S2 instance, we can control the frequency, but independently controlling the S3 and S4 and the phase difference between that switching sequence of pole A with respect to pole B, by controlling that one we can control the output voltage also. Here we have done that way. Here it is shown how to control that. This is the pole VA0. So, here that like the half bridge converter, we are not splitting the DC link into VDC by 2 into VDC by 2. Instead of, we are measuring the AB with respect to a common point O. O we assume to be at the center point of the DC link. So, fictitious center point, that is we call the VA0. It will again, it will be VDC by 2 minus VDC by 2, and given a delay. The previous circuit, if you see here, we have given full 180 degree for S1 and S3 on. Okay. When this S1 is on here, S3 is on here, the red line. Okay. So, 180 degree we have given here. Now, instead of 180 degree, slightly less than 180 degree we have given here. Okay, this alpha. So, the moment alpha is given, there will be a period during which both S1 and S3 are conducting. S1 and S3 are conducting means A and B will be shorted to this point. So, output will be 0. So, that 0 point, that 0 interval is placed symmetrically between these notches. Okay. So, increasing the alpha, this notch width increase on that pulse point, this will slowly reduce and the output fundamental will reduce. Then we found out the harmonics, how to find out the harmonics, and we found out the how the fundamental varies. So, we found out fundamental will be proportional to alpha by 2. Okay. So, we got a voltage control by varying that overlap angle alpha, but it is not proportional to alpha, it is proportional to cos alpha by 2. So, for any linear control, we want a function which is proportional to the output fundamental we want. So, there we said we will talk about the sine triangle PWM. So, before coming to sine triangle PWM, let us go to, this is only for single phase. Okay. How we can get three phase inverter? We study the basic operation. Okay. So, previously let us see all this three phase operation is the proper extension of our single phase half bridge converter. So, this three phase structure can be realized by properly extending our single phase half bridge converter. Half bridge inverter. See, let us again go back to our basic inverter scheme. VDC by 2, VDC by 2. Okay. This is our center point O. We have the switches. It is assumed that it is bidirectional. Freewheeling diode is also there. Now, we have the A here, pole A, okay. And we said we can add any number of legs to this inverter, and each leg can be independently controlled and it is not related to the switching of other leg. So, for three phase, what is the next we should do? We should add three more legs here. So, this is A, this is our three more single pole. So, this is C, single pole double throw switch. That means, this pole B can be either connected to this point positive rail or to the negative rail by appropriately switching the devices. Now, where we connect the load? So, let us take same this point. We connect it here. This is B. What will happen to C? Again C will be we can do it this way. Then we want a three phase inverter. Three phase we require means we require symmetric three phase. That means the waveform should be exactly same, the positive half or negative cycle, but that is the amplitude and the duration. Also, the B and C phase should be appropriately phase shifted. Three phase it is should be B phase should be 120 phase shifted with respect to A, and C phase will be 120 degree 240 degree phase shifted with respect to A. So, that means B, the pattern, the VB0 phase shift or the switching sequence should be, or the switching sequence, switching sequence should be (120) phase shifted with respect to A, that is delay. It is a delay of 120 degree. with respect to VA0 waveform. Okay. Then what will be for phase C? And VC0 phase shift to 40 degree or 120 degree with respect to VBO or 240 degree delay with respect to VA0. Okay. So let us draw the pattern. Now let's go to the next page. So for the reference, let us again draw our inverter basic schematic here. This is A, this is our load for A, O0, VDC by 2, then B, then C. Is connected here and the load is connected here. Okay. Let us draw the waveforms. Now VA0, this is our VA0 x-axis. So let us take 190 means this much. So VDC by 2 here. Okay. So we have 3 here, 3 here, again 3 here, 3 here. So minus VDC by 2. Okay. This is our VA0. Okay. So here S1 on or top switch is on. So this is 1. Okay. And when the bottom switch is on, we have minus VDC by 2. So this is plus VDC by 2 from here to here, and from here to here it is minus VDC by 2. This we have studied last class. Now what we want, the same sequence. So we are talking about each pole, the top switch and the bottom switch. Now let us draw the B phase. So for clarity we will use a different color. Let this be the axis for the B phase. So 120 degree phase shift. We know that this is 0, this is pi, and this is 2 pi. So 120, this is pi means this is pi by 2. Okay. So this we can divide into 3 divisions. So this is 60-60 each. So 120 means it will come here. So after the A phase top switch is on, 120 degree phase shifted, we should start the pole B operation. So, after 120 degree again the top switch is on. So, again here it will go like this. So, when the bottom switch here, when this is turned on, it is minus VDC by 2. Only thing, the durations for the top switch and bottom switch of A and B is the same, only the sequence is delayed by 120 degree. It goes like this, okay. So, this is the pole B with respect to the fictitious center tap VB0 plus VDC by 2 minus VDC by 2, okay. VB0. Okay. Now, VC0, let us take a different color for VC0, let us take green, this is the x axis. So, it should be the top switch of the the starting instant for the C phase should be 240 from A or 120 from B. So, 120 from B, this is 120, 120 means 2 pi by 3. Okay. 120 means again here, this is 120, one more 120 means it will be from here, this 240. So, C phase starts from here. Okay. Now, this is the pole voltage C, that is VC0 shape. So, if you see the shape, the positive amplitude, positive duration for the A phase, B phase, C phase are the same, they are same waveform, but there is a time delay or a phase shift of 120 degree with respect to each other is there. Okay. Now, here also like before our single phase half bridge converter, it has the fundamental V harmonics. If you say it has the fundamental, third, fifth, seventh, ninth, all harmonics will be there for each pole voltage waveform. Okay. Now, as I told, we are more interested in the fundamental and we want to suppress the low frequency, high amplitude, low frequency harmonics as much as possible. So, the next after the fundamental, the most predominant harmonic is 3. It has the amplitude inversely proportional to the harmonic. So, it will go like this. If fundamental is there, third will be here, fifth will be here, this way it goes. So, how we can eliminate the third harmonics? Is it possible? Let us start with third harmonics. See, third harmonics, if you see here, fundamental moves by 120 degree. Okay. When the fundamental moves by 120 degree means, that is let us say the fundamental for this one is something like this. Okay. The third harmonics, how much it will move? Third harmonics, how to find out? For fundamental 120 degree, for third harmonics, it will be 360. That means third harmonics, if the third harmonic starts from here, 120 degree, see it will be again here, it will go like this and come here. So, 120 degree from here, it is the same thing as if it's starting from here. So that means third harmonics is concerned, it will be in same phase. So if you draw here, here also if you see here the third harmonics, this is the third harmonics for this one. Okay, we will draw with this is the third harmonics. And what about the third harmonics for this one? Third harmonics for this one, from here to here, if it is starting from here, third harmonics here, 120 degree, it will have the same effect. Okay. So third harmonics, if you see, so let us say third harmonic starting from here. So that means the third harmonics for all the three phase waveform are in same phase. Okay, because 120 into 3 is equal to 360 degree. Okay, so this waveform also from here to here it is 120 degree phase shifted. So starting from here, it is same exactly the way starts here, it will starts here. So if you see here, all the third harmonics are in the same phase. There is no phase shift. So this will be true for ninth multiple of 3. Ninth, okay. All these are 3 ninth, then what you say, multiple of 3 is 27. All these harmonics, okay. 15, all odd multiple will have all the multiple of 3, 3, 9, these type of harmonics will be in the same phase. So these are all called triplet order. Anyway, because of the symmetry, triplet order, even multiple, 6, 12, all those harmonics will not be there, because the waveform has odd symmetry. For 6 and 12, it's even symmetry. Even symmetry means if you take the waveform, the center point left half and the right half will be same. But here the left half and right half will be the same, but it's inverted. So it is called odd symmetry. So all the odd multiple of 3 will be absent here. That means all the triplet order will be absent here. Sorry, triplet order will be in the same phase. So all the triplet order harmonics are in phase in all the pole voltages. Okay, in the pole voltages. Pole voltages. So they are in same phase means, if you see here, let us say the voltage waveform is like this. Due to this voltages, if the current exists, the current will be, if you see here, the sum of these 3. The sum of these 3 waves, only triplet order, if the current exists or the harmonics is V third, V3, VS0 third plus VB0 third plus VC0 third. If you add all these harmonics, it is not 0. For symmetrical 3 phase, what we used to say, VAN plus VBN plus VCN, phase voltage should be 0. But if you see, this is not 0. So for this connection, IA plus IB plus IC, triplet order, if you see the current will be coming in same phase. So if IB is coming in this direction, the IA triplet current will also be in this direction, and triplet order of C phase also will be in this direction. It will sum here, and it is not 0, so it will come back to the phase through the DC link, okay, if the current exists there. Now, suppose if I break this one, okay. Now, this is for the triplen. Now, if I draw the fundamental, let us draw the fundamental with a different color. Fundamental here it is drawn. This fundamental will be approximately like this. Here the fundamental will be like this. If you take the fundamental, 3 fundamentals, if you sum it, the VA0 1 plus VB0 1 plus VC0 1 will be 0. Triplen will not be 0, the fundamental will be 0. For 5th and 7th, 5th and 7th will also will be 0. So, if all this, if I break this one, the triplen current which is coming here this direction, they will sum here, and if you remove this connection to the central point, what will happen? There will not be any return path for the triplen. Okay. So, what is mean by this one? So, let us redraw this one again once again. This is A, this is B, this is C. Okay. So, we found for the load, we will draw it in a different way. This is A. This is B and this is C. Previously, this point we are connected to O. That means, previously this point was connected to this side. Okay. So, we found the, if the current triplen, that is IA3, IB3 and IC3 means triplen order, all will come here, it is not 0, it will sum up and it will go like this. Okay. So, when this connection is there, the triplen order will go here, that is in this current will be IA3 plus IB3 plus IC3. This current will flow through this point. These triplen voltages are there, they are in the same phase across this one. Now, if we remove this one, that means I will remove this path. Then what happens? The triplen order, 3rd, 9th, 15th, all that order, currents will not flow through, even though voltage is present. What do you mean by voltage is present? Still our VA0. VA0 is like this. We will draw once again. This is our VA0. This is our VA0. Even though that center point, fictitious center point connection is removed, that is this connection, broken line we will show, that shows this is removed. this connection is removed. So, still we can, according to our switching sequence, we can turn on top and bottom, and we can measure the voltage with respect to A0. VA0 is like this, and VB0 120-degree phase shifted. So, let us draw the VB0 waveform. After 120-degree phase shifted. So, it will be starting from here. Okay. And VC0 waveform will be here. See, VC0 120-degree phase shifted with respect to B or 240. So, it will start from this is 240. This is our VC0. Okay. Now, if you see here, let us mark these 60-degree points. These are the 60-degree points. Here also. Okay. Here the 60-degree points are. Okay. So, what we did, we removed the triplet order harmonics current by removing this connection. So, without using filter, a simple connection removed all the triplet order currents, but triplet order voltages are there in the pole voltages. That means, by removing this connection, now this, let us mark this point as N. So, this is our N. So, the connection by removing the connection NO, all the triplet order currents are 0 through the load in the IAIB IC. Okay. So, by removing this one, but still the pole voltages are same. That means, in our pole voltages VA0, VB0, VC0, all the triplet order voltages will be there. So, what we are more interested in the current. So, now in this phase current IAIB I3, we have only fundamental, 5th, 7th, 11th, 30, all these harmonics only will be there. Now, the question is, previously with the NO connection, our load voltages and the pole voltages were same. Now, the load voltages and VAN, now the load voltages are VAN, VBN, VBN and VCN. So, we have to find out what is VAN, VBN, VCN, load voltage. How to find out? Let us find out. VA0 is known. VA0 is equal to, if you measure, it is okay, VAN plus VNO. Okay. Previously, because of the connection, VNO was 0 because shorted. Now it is open, so there is a voltage VNO. Okay. Now what is VB0? VB0 will also be equal to VAN plus VNO. VC0 also is equal to VAN plus VNO. Okay. But what we want is VAN, sorry, oh, this is VB0 is equal to VBN. VC0 is equal to VCN. Let me correct it. This is VCN. Okay. VNO is the same. What we want VBN, VAN, VBN and VCN. Okay, how to find out? See, I said in current which is passing through IA, IB, ICR 1/5, 7, 11, 30 harmonics. And we know for a three-phase system, the triple nodal will not be 0, all the fundamental will be 0. And we can see all the harmonics 5th, 7th, 11th, 13th. If you take the 5th, 7th, 11th, 13th harmonics individually from VAN, VBN, VCN, this will also sum to 0. But VA0 contain triplet. But this waveform VAN, VBN will not contain triplet order. So according to Kirchhoff's law, where the triplet order will be? The triplet order will be always dropped across NO. So all the triplet order will be dropped across VNO. So before coming to that one, see we have marked the switches, but we have not numbered it. So let us take starting from omega t is equal to 0, starting from here. We are turning on the switch, top switch of phase A. So this is 1. After that, after 120 degree, top switch of B is turned on here. The next turn on. So here it will be, this is 1. So at this point omega t is equal to 0, we are turning on phase A, top switch. Okay. So 1 is marked top switch. Then after this one, the transition happens here. That means VC0 going from positive to negative. That means at this instant, the negative C phase, C pole switch is turned on. So this will be number 2. Negative means this one. This is number 2. Then after this again we are turning on B phase top switch. So this is top switch is number 3. So 3 is here. So here we have 1, here you have 2, here we have 3. Then after this, here we are turning on the bottom switch of A phase. So this will be 4. So this we can say 1, this we can say 2 full this duration, this will be 3, this full duration will be 4. So this is 4. So here we are turning on 4. After 4, we are turning on this side. That is top switch of C phase. This is 5. So this is 5. So let me correct this one. Okay. So 5 is here. Now after this one we are turning on the bottom of B phase. So this is 6. So this is 6. So the sequence is same like that is 1, 3, 5, 4, 6, 2. So top switches are marked 1, 3, 5, 4, 6, 2. And you can see every 60 degree there is a change. That is true also for symmetric operation. There are 6 switches. So in a symmetric way, if you have to turn on the switches every 60 degree, you have to turn on a switch and turn off a switch. So this sequence is 1, 3, 5, 4, 6, 2. Now as I told before, this pole voltage waveform VA0, VB0, it will contain fundamental, triplen, all the harmonics. But the moment NO is removed, all the triplen harmonics are, harmonic currents are removed. Now the new load voltage waveform VAN is equal to, the relation is VA0 is equal to VAN plus VNO. So if you do the Kirchhoff's voltage law for the loop, VA0 contain all harmonics. So these harmonics should be dropped either in VAN or VNO. Okay. Now VAN, since the NO is removed, VAN will not have triplen order harmonics. So VAN should not contain VAN triplen order voltages also. If voltage is there, there should be a current and drop to take care of the Kirchhoff's law. So here what happened? VAN will not contain all the triplen order. So where the VAN will go? VAN will all go to VNO. VNO contain all the triplen order. Okay. Now we want what is we want to find out VAN, VBN, VCN. Let us find out. So VAN, VBN, VCN. So we have got the pole voltages. VA0 is equal to VAN plus VNO, and VB0 is equal to VBN plus VNO, and VC0 is equal to VCN plus VNO. Okay. Now we know that all the triplen order will be drop across VNO. So for, if you sum it, VA0 plus VB0 plus VC0 is equal to, we know VAN, VBN, VCN will not contain the triplen order. So all the harmonics, when you sum it with the 120 degree phase shift, including the fundamental, it will VAN plus VBN plus VCN will be 0, and triplen order it is not 0, they are equal, so it is 3 VNO. So this shows the value VNO. VNO is equal to 1 by 3 VA0 plus VB0 plus VC0. Okay. Now let us substitute this one to this equation 1. Let us see, this is 3, this is 3, this is 4. So substituting equation 4 in 1, now our new VA0 is equal to VAN plus VNO is equal to 1 by 3 into VA0 plus VB0 plus VC0. Okay. That means VAN is equal to VA0 minus 1 by 3 VA0, because this has to go to other side, okay, and minus of 1 by 3 into VB0 plus VC0. We can write it like this. This is equal to VA0 minus 1 by 3 VC, 2 by 3 VA0 minus 1 by 3 VB0 plus VC0. This is equal to our VAN voltage. So in a similar way, we can write down the VBN and VCN also using the symmetry. So what will be VBN? VBN is equal to again 2 by 3 VB0 minus 1 by 3 instead of VA0 plus VC0. Similarly, VCN also we can do it. Okay. Now let us draw what is our VAN waveform. VAN is equal to 2 by 3 VA0 minus 1 by 3 VB0 plus VC0. Let us go back to our waveform. We will try to draw that. See, let us draw the waveform. See, VAN, if you know, we can find out VBN, VCN also, because 120 degree phase shifted. So, let us take VAN, first 60, these are the 60 degree points. So, first 60 degree, that means this is equal to 2 by 3 VA0. Let us take VAN is equal to VB0 plus VC0. So, first 60 degree VB0 and VC0 are equal and opposite, and it will cancel. So, VAN will be 2 by 3 VA0. 2 by 3 VA0 means this is VDC by 2. VDC by 2 into 2 by 3 is equal to VDC by 3. So, let us take VDC by 3 is this much. Okay, because that is equal to 2 by 3 VDC, 2 by 3 VA0, 2 by 3 VA0 is VA0 equal to VDC by 2. Okay, 2 cancel and VDC by 3. Now, during the next 60 degree, that is from here to here, from here. So, from the next 60 degree, if you see VB0 and VC0 are in same phase. So, VA0 plus VB0, VA0 plus VB0 will be minus of, because both are minus, VDC by minus VDC by 2 minus VDC by 2. So, minus VDC. So, the VA0 plus VB0 will be minus of 1 minus 1 by 3 into VDC, minus VDC. So, it will be equal to 1 by 3 VDC, and here again it will be 1 by 3 VDC by 2. So, here if you see here, this will go to 2 VDC here. So, this will be 2 times into VDC by 3. Again if you see here, it will be like this. So, the waveform will be, if this is the x axis, the waveform will have a shape like this. Every 60 degree there is a change and it goes like this. And this duration is VDC by 3 amplitude, and this amplitude is equal to 2 VDC by 3. So, this is also called a 6-step waveform. Why? For one cycle, that is from here to here, there are 6 steps are there. This is 1, 2, 3, then 4, then 5, then 6, it comes here, starting point. Again it starts here, 1 level. So, 6, these are all called, this is all called a 6-step waveform. Okay, this waveform will contain fundamental, fundamental, 5th, 7th, 11th, all harmonics. All the triplen will not be there. This is our VAN waveform, VAN. VB and VC will be 120 degree phase shifted. So, if you see here, to get this 6-step waveform, we have not done anything, we are only a very simple thing. The VNO connection, the neutral connection we removed, that is we only removed this neutral connection from here to what is the connector center point. Okay. Once you remove that one, all the triplen order harmonics are removed, because triplen order harmonics are in same phase. So, it will sum up. So, unless there is a return path, it will not be able to flow. So, by removing the return path, that is connecting this point to this O point, we are removing the triplen order. But in the pole voltage waveform, the triplen harmonics are there. Now, the question is, what is our phase voltage waveform. So, the phase voltage waveform, that is VAN. VAN plus the triple in order will be VA0. So, all this NO, VAN will be dropped across the load neutral point and the our DC link midpoint we can measure. That will give the triple in order voltages. And the phase voltage we got like this. So, here all the triple in order harmonics we have eliminated. But in many of the motor drive applications, we have to eliminate other harmonics also, low order, 5th, 7th, 11th, 13th. At the same time, we have to control the fundamental. So, how we can do this one? What is the technique we have to use it? See, here also, because the pole voltage, we can do independent switching and we are using equal degree on, equal duration off. But how to control the amplitude? To control, now if from this waveform, if you want to control the amplitude, we have to change the DC link. But DC link changing is very difficult. Suppose a battery operated vehicle for high dynamics, we cannot keep on changing the battery. So, DC link we call it a stiff DC link. But for many motor drive applications, along with the frequency, the fundamental amplitude also we have to vary. At the same time, the harmonics also we have to suppress. Now, the triple in order we have eliminated, but still the other harmonics are 5th, 7th. How to suppress? There again we use the PWM technique, sine triangle PWM technique, or other PWM techniques are there. We will study various PWM techniques in the coming classes.